Chapter 9, Sampling and Interval Estimation. Sampling is a part of inferential statistics. With inferential statistics, we are using a representative sample to answer questions about a characteristic of a population. The idea is that the population is too large to measure every single individual. And so what we do instead is we collect a sample of less than all individuals, and with that sample, we measure the characteristic. And then we use that measure on the sample to postulate what the characteristic would be like for the entire population. Population parameters are summary measures of the characteristic of the population, and the sample statistics are the summary measures of the characteristics of the sample. So we collect the sample and then we calculate the sample statistic, and we use that to project the value of the population parameter. Sampling methods are methods of obtaining a sample that is representative of the population. There are several different methods, and we want to use the best method for the given situation. One method is a simple random sample, or an SRS. The simple random sample ensures that every individual has an equal chance of being selected. It is the most basic sampling method, but is not always appropriate. An example of simple random sample is drawing names from a hat to determine which 10 individuals will be interviewed. Because everyone's name is on a piece of paper in the hat, everyone has an equal chance of being selected. Stratified sampling is intended for sampling when the population has subgroups or strata. An SRS subsample is then taken on each of the subgroups. The size of each subsample can be equal, or it could be proportional to the population size for each subgroup. For example, student opinions. There are more freshmen than sophomores, and more sophomores than juniors and seniors. Different classmen likely have different opinions on issues. So, for example, if you have a population of, say, 50,000 students in the school, and you need a sample of 2,000 students, if you use an SRS, it could be that all 2,000 students are freshmen. Then you don't have a representative sample because you're only going to get the opinions of the freshmen. A stratified sample could be used to ensure representation by each of the classes. So, for example, you could have a certain number of freshmen and a certain number of sophomores and juniors and seniors. So, for example, you could sample 500 freshmen and 300 sophomores and 100 juniors and 100 seniors. And then you've ensured that you're going to have representation from each of those groups. You can have equal representation, or you could have proportional representation. Cluster sampling is intended to make representative sampling easier. If the population is made up of multiple groups of similar composition, you may not need representation from all of them. An SRS can be used to select which groups you're going to sample, and then all individuals in the selected groups are sampled. So again, let's look at student opinions. Because third grade students are simply divided into classes, there is a similar composition of students in each of those third grade classes. It may not be necessary to sample from every single third grade class in the school in order to get an idea of the opinion of third graders. You might use an SRS to select a few third grade classes and then survey all the students in those selected classes. An in-class survey will likely take up as much class time if 5 students are completing the survey as if all the students in the class are completing the survey. So you might as well pass out a survey to all the students and have them all completed at the same time. Systematic sampling is intended for manufacturing type processes in which individuals are passing by the researcher rather than all available at once. Because it is a process, we may not know the population size or be able to label individuals prior to sampling, so we can't do an SRS. In systematic sampling, the sample is chosen by selecting every kth individual in the process for a given period of time. One example of that is the election exit polls. The exit polls are conducted by individuals standing outside of the polling booths, interviewing voters as they exit. The number of voters who will actually vote at any polling place is unknown until after the voting has ended. pollsters only have access to the voters after they have exited the polling place, so they may choose to interview every fourth person to leave the polling place. The frequency, K, is predetermined based on a required sample size and the estimated voter turnout. When doing systematic sampling, you want to watch out for cyclical manufacturing processes. Maybe you have coins that are coming out of 4 different molds, and if you're always checking the fourth coin, you're always checking from the same mold, and so coins coming from the other 3 molds are never being inspected. So you may want to make sure if there's a chance of a cyclical process that you're taking that into account, and maybe you're not using every kth individual, maybe you're mixing it up a little bit in addition to that. If you think about the simple random sample, the cluster sampling, the systematic sampling, and the stratified sampling, they're essentially ideas and they're types of sampling processes, and in many cases researchers will combine different aspects of these different processes in order to do their sampling. And so, for example, with the exit polling, you may use cluster sampling to determine which polling places you're going to choose to send someone to. But then once you get to those polling places using your cluster sampling, next you may use a systematic sample to interview every fourth person that comes out of the polling place. So researchers will combine and mix these different sampling processes when they have larger studies that they need to take into account. Convenience sampling is simply a sloppy sampling method without much hope for results that will be representative of the population of interest. Convenience sampling is always the easiest because essentially we are finding ways that are the easiest to sample. Examples of convenience sampling are online polls, friend polls, and surveying at high traffic locations. For example, there are a lot of online polls that request individuals' opinions regarding an issue. However, the only individuals able to respond to those polls are individuals who visit those certain websites. Friend polls are biased because when we ask our friends their opinions, we already are going to get opinions that are similar to our own. Surveying high traffic locations can be helpful if we need a certain sample size, but people that are at those high traffic locations are there for a reason, and individuals who are not there for a reason. You want to make sure that you're representing both groups. Typical research involves a researcher collecting one sample and using sample statistics to make inferences about the population parameters. What would happen if another researcher repeated the same study with a different sample? Assume we are conducting research in which a sample of n equals 10 individuals is to be selected from the population, and the sample mean is to be used to make inference to the population mean. The sampling distribution is then the set of all possible sample means that could be collected from that population by taking all possible samples of size n equals 10. The sampling distribution helps us understand how likely observed results are based on all possible results. Consider this group of 10,000 customer satisfaction ratings. That is our population. We would only know this information if we surveyed all 10,000 customers. Now here we're going to assume that we have the information on those customers and that the mean is 23.2 and the standard deviation is 11.9. From that population, for our study, we collect a sample of n equals 100 customers to survey. Once we have done that, we calculate the sample mean and the standard deviation. We'll suppose that our sample mean came out to be 23.3 and our sample standard deviation came out to be 11.5. If you look at the population values, you can see that our sample values are fairly close. Next, let's suppose that a second researcher repeats the sampling process and collects a second sample of 100 customers. Not necessarily the same 100 customers that were in the first sample, but there could be overlap. This time, the sample mean is 24 and the sample standard deviation is 12.5. Again, these values are similar to the statistics found in the first sample and similar to the population parameters, but they're not the same. This process could be repeated over and over by many different researchers. Each time, these researchers would get a slightly different result. From a combination of all those different results, we could come up with this graph. This new graph is made up of the thousands of sample means that would result from the thousands of possible samples of size n equals 100 from the population. Notice that the graph has a bell shape to it, even though the population graph did not. Our population graph looked a little bit uniform here, then it had a peak here on the right, and then a little bit of skew. So it definitely does not have a bell shape. But the distribution of the sample means does. This distribution of sample means is referred to as a sampling distribution. It is considered a population of all possible sample means and has its own parameters, mean and standard deviation. What do you notice about the mean? The mean is exactly the same as the mean of our original population, 23.2, 23.2. What about the standard deviation? The standard deviation for this sampling distribution is actually equal to the standard deviation of our population divided by the square root of our sample size. So the standard deviation of our population is 11.9. Our sample size was 100, so the square root of 100 is 10. If we take this standard deviation of 11.9 and divide it by 10, we get 1.19, which is the standard deviation of our sampling distribution. The central limit theorem formalizes those concepts. Given a population with a certain mean and a certain standard deviation, the shape of the distribution of the sample means for a large sample size will be approximately normal or bell-shaped in appearance, with mean equal to the population mean and standard deviation equal to the population standard deviation divided by the square root of the sample size. What is the mean and the standard deviation? 23.2 and 11.9. What is it for our sampling distribution? 23.2, exactly the same as what we had here, and 1.19. Where does that 1.19 come from? This 1.19, if we look here, it says it's equal to the 11.9 from our population divided by the square root of 100. So we have the standard deviation of the population equals 11.9. We have n equals 100. And on the second page, we have this formula right here of the standard deviation divided by the square root of n. Well, if we write that right down here, standard deviation divided by the square root of n, and then we plug in the numbers, we have 11.9 divided by the square root of 100. Well, the square root of 100 is just 10, so we have 11.9 divided by 10, and that's just 1.19. We just move the decimal over. And so that's where we get this standard deviation. The standard deviation for the sampling distribution is found by taking the standard deviation of the population and dividing by the square root of the sample size. Isn't that neat how that just comes out? The mean and the variance of the sampling distribution may be denoted as mu with an x bar in the subscript and a sigma with an x bar in the subscript. And so instead of the mu and sigma that we had for the population, we're changing it to mu x bar and sigma x bar for the sampling distribution because we want to recognize that there is a difference between the standard deviation for the population and the standard deviation for the sampling distribution. And so we're just adding a little detail to make sure that you don't mix the two up. Consider these two different populations. Here we have a population that is skewed severely. It has a mean of 50 and a standard deviation of 50. Here we have a uniform distribution that has a mean of 45 and a standard deviation of 8.7. If we select thousands of samples from this population, and each time we calculate a sample mean from that sample, those thousands of sample means will produce their own distribution. If the sample is of size n equals 5, the sampling distribution will look like this. You notice that it's getting to be a little bit more bell-shaped than the population that we started out with. If the sample is of size n equals 15, it is even more so a bell-shaped curve. But you'll notice that there is still some right or positive skew to this distribution. Now let's look at what happens with this uniform distribution. If we take a sample of size n equals 5 and compute the sample mean, and we do that thousands of times, then our thousands of sample means are going to form this bell-shaped curve. We can do the same thing with samples of size n equals 15, and again we get a bell-shaped curve. What you will notice is that the mean of our sampling distributions is equal to the mean of the population distribution. The standard deviation of the sampling distributions is equal to the standard deviation of the population distribution divided by the square root of our sample size. So how big does the sample size need to be in order for our resulting sampling distribution to have a bell shape to it? You'll notice that here n equals 15 was not large enough for us to get a bell shape. We have somewhat of a bell shape, but you can see it's still skewed to the right. Here, a sample of size 15 was enough. In fact, even a sample of size 5 looked pretty good. The sample size required in order to get a bell shape to our sampling distribution will depend on how skewed our original population is. And it could be as low as n equals 5 or as large as n equals 100,000. Now let's take a brief look at some of the symbols that we're using. X bar is x with a line over it, and it represents the sample mean and is calculated from the sample. S is the sample standard deviation and is calculated from the sample. Mu is the population mean and is typically unknown, but if we know the population, then we could compute the population mean by simply computing the mean of all the values in the population. Mu with a subscript of x bar is the mean of the sampling distribution and is typically unknown. However, we know that by the central limit theorem, this value is equal to the population mean, which is mu, this value up here. Sigma is the population standard deviation and is typically unknown. Sigma with a subscript of x bar is the standard deviation of the sampling distribution and is also typically unknown. However, we know by the central limit theorem that this value is equal to sigma over the square root of n, where this is our sigma. S sub x bar is the estimated standard deviation of the sampling distribution of the sample mean, but is more commonly referred to as the estimated standard error of the sampling distribution, which is equal to the standard deviation divided by the square root of n, just as it was here, except in this case we're using a sample standard deviation instead of the population standard deviation, which we would typically use because we typically know the sample standard deviation and not the population standard deviation. Capital N is the population size and is typically unknown, and lowercase n is the sample size and is known from the sample. Now let's look at confidence intervals. Confidence intervals are intervals that are intended to capture our population value. So if we think of a confidence interval for a population mean, we're intending to know where our population mean is. But typically we don't know where that population mean is. We can use a sample mean to estimate where that population mean is, but we're typically going to be wrong. We'll be close, but wrong. And so often what people like to do instead of looking at a single sample mean is compute an interval. A confidence interval will capture the population mean with a certain amount of confidence. So for example, if we did this with the customer satisfaction rating data, the researcher can be 95% confident that the true mean customer satisfaction rating is between 21.046 and 25.554. In fact, the population customer satisfaction mean rating is 23.2, so this interval really does contain that population value. If we were to just find the estimate, so just the sample mean, then the sample mean that we had was 23.3 the first time we took a sample, and the second time it was 24. And so it wasn't 23.2. We were wrong. But our interval is right because it is within the interval. People tend to like that better than just coming up with a single value and saying, well, I think it's close to this. They'd rather have an interval and say, I'm pretty sure it's within this interval. Confidence intervals, however, are not always 100% accurate. We can only be 100% confident if we actually know what the population mean is, or if our interval includes the entire possible set of values. So you could say, well, my interval is from minus infinity to positive infinity, and then you know that you're accurate, but it's not a very useful interval. Confidence intervals are made up of parameter estimates and a margin of error. So the parameter estimate might be our sample mean, and the margin of error is our level of confidence in where we think that population mean is. It provides a degree of accuracy to our estimate. So, for example, with political polls, the media might report that candidate A has 75% of the vote, while candidate B has only 25% of the vote. The margin of error on this poll is 3%. What does that exactly mean? Well, it means that candidate A of 75% plus or minus 3% could have as low as 72% of the vote or as high as 78% of the vote. They're not really sure because all of the votes have yet to be counted. The pollsters are 95% confident the true percentage of the voters who voted for candidate A is between 72% and 78%. Only once all of the votes have been tallied will they know exactly who won the election. But people like to know beforehand, or at least they like to anticipate or get an idea of who's winning, which is why they conduct these political polls. And so they have to have this level of accuracy because they don't have all of the votes. And so they're estimating from the votes that they do have, or the responses that voters have given them as to who they voted for, what the actual vote outcome is going to be. But there is that plus or minus margin of error that means that, well, because all the votes haven't been counted, we could be off by a little bit. So when you look at the percentage of votes that each candidate has, and it looks like from the margin of error that those percentages overlap, that is when the polling media says the race is too close to call. When the interval does not overlap for two different candidates, that is when they call the race for one of the candidates. Let's take a look at some graphic from the recent Republican presidential primary. Consider this one from South Carolina, where with only 7% of the vote counted, the election was called for Newt Gingrich. If you look at the proportion of vote for the top two candidates, it looks very close. So why, with only 7% reporting, are they able to call the projected winner? I think with this one they used some subjective probability assessment and used other information besides just this poll in order to determine that Newt Gingrich was going to win that state. Perhaps the fact that this was his home state is why they felt like they could call the race so soon. Let's take a look at the Michigan primary. Here, with only 28% of the reporting, it looks like the race is pretty close, and so you can see they haven't called the race for either candidate. Now with the race at 59% reporting, you can see that there's a little bit more distance between the top two candidates, but still they are not calling the race for the top candidate. It's interesting to look at the map of the different counties and to see that there's a whole lot of purple here, which represents Rick Santorum. And so you would think that he would be winning the primary. Why is he not winning? Because there are more counties voting for him, but those counties voting for him are the counties with the smaller populations. Those counties with the higher populations had voted for Mitt Romney. And so by popular vote, Mitt Romney is in the lead, even though by looking at the colors, there are more counties that were voting for Rick Santorum. Here's a good example. This county of Hillsdale has very few individuals in it. It looks like maybe 10 to 12,000, and Rick Santorum is winning in that county. But because you've got other counties that include cities like Detroit that would have populations in the tens, if not hundreds of thousands, and those were voting for Mitt Romney, that's why overall he had the popular vote. So think about different sampling methods and how if you chose the wrong sampling method, you might actually assume that Rick Santorum was going to win this state's primary. Now with 74% of the vote counted, they are projecting Mitt Romney to win the state of Michigan. So essentially, the margin of error at this point is small enough that there's no overlap between the 41% and the 37%. And because there isn't any overlap, they feel that they have enough information on the true proportion of individuals in the state who are voting for those two candidates that they are able to call the race at that point. Here's another graphic that I thought was very interesting. With 0% of the reporting, they've already projected the winner. How do you think that's possible? Well, part of it, again, may be subjective probability assessment and just knowing that Romney had an enormous lead in the polls leading up to this primary. This is a confidence interval simulation applet. And what it is designed to do is give us an idea as to how confidence intervals work and what they really mean. We can choose our sample size right here, and then we can look at a number of confidence intervals. So here we have a sample of size 10, and it says when you click the sample button, 100 samples of that size will be taken from a population with a mean of 50 and a standard deviation of 10. So the mean is actually 50, and we're wanting to capture 50 within our confidence interval. Well, we're going to take a sample of size 10 and create a confidence interval, and that interval may or may not include the actual mean of 50. For a 95% confidence interval, we expect the proportion correct to be about 95%. For a 99% confidence interval, you expect the proportion correct to be about 99%. But we'll have to do this many, many times. So we'll click on sample, and what you see is you've got yellow lines, and then you've got blue lines on the, or blue tips on the ends of these lines. Well, the yellow lines represent the 95% confidence intervals, and the blue tips represent the 99% confidence intervals. Because you want to be 99% confident, you want to be more confident, you have to have a wider interval. And so this vertical line represents the true value of the mean, which is 50. And so we're looking at which of these intervals actually have 50 inside of them. Of the 100 intervals in this list, we have 99 that contained the 50 of these 99% intervals, and 93 of the 95% intervals were right. So 99% correct and 93% correct. And we expect them to be close to 99% and 95%. So you can see there are a couple here that were wrong. The ones in red are 95% confidence intervals that were wrong. The white one right here indicates a 99% confidence interval that was wrong. So even though we say we're 99% confident, this researcher was still wrong. And so that's something you have to keep in mind with confidence intervals, is there's always a chance that your interval is wrong. 99% or 95%, those are pretty good odds. I mean, being right 95% of the time, that's pretty good. People seem to be okay with that. Now let's see if we click on the sample several more times. It does this over and over and over again, and each time it's collecting samples of size 10. So each one of those lines is a confidence interval made of 10 values. And each time we've got some that are red, meaning the interval did not contain the mean. And we have some of these white tips, which means that the 99% confidence interval did not contain the 50. And so overall, you can see these proportions correct changing. So here now we're at 0.992 for our 99% interval and 0.947. So we're actually getting closer to 95% for this setup. Do it a few more times. You can see sometimes we have a few intervals that are not right. Sometimes we have lots of intervals that are not right. Here's a whole lot of intervals that were not right. And sometimes we have very few intervals that are not right. Most of them are correct. Here we have lots of white tips. So our 99% intervals, here's several that were incorrect. But I hope what you take away from this is that With a confidence interval, you as a researcher, you're only calculating one of these, not 100 of them. So if your interval is one of these yellow ones, then you're in good shape. If it's one of the red ones, well, then your research is actually wrong. And we hope that 95% is good enough that we're doing a good job with our research. And so we tend to be okay with 95%. It's very difficult to be 99% accurate. It's very difficult to be 100% accurate. If we can be 95% accurate, that seems to be good enough for most research because it's based on how big of a sample we can collect and different things. And if we can't survey the entire population, then that's the best we can do. So these are 95% and 99% intervals, and as a researcher, you only compute one of them, and you hope it's one of the yellow ones or the blue ones and not one of the red or the white ones. William Seeley Gossett was a researcher. He worked for the Guinness Brewery. He decided that there had to be a way that they could get more accurate intervals and hypothesis tests for sample means when they had really small sample sizes. The problem is with the work that he was doing, they always only had a few data points that they could sample for their research. That will happen in cases where you're dealing with human subjects or where you're dealing with products that are very expensive or scarcity of the product that prevents you from collecting a large sample. A normal distribution didn't tend to work for Mr. Gossett because he was dealing with very small sample sizes. And if we go back to our central limit theorem here, it says for large sample sizes. Okay, so we'll have a bell-shaped curve when we have large sample sizes, but not when we have small sample sizes. So we're not going to get approximately normal when we have small sample sizes. Here's an example. If we only have 5 individuals, we're going to get a skewed distribution situation. And so we may not be able to use our methods that we came up with in the normal distribution. William Seeley Gossett created an adjustment for the distribution that would work with small sample sizes. And here's a paper. This is a very famous paper that he wrote in 1908 about it. It's referred to as the t-distribution. Sometimes it's called the student's t-distribution because he wasn't allowed to use his name in his research, and so he had to put his name as student in his publications because the company was having problems with things that people were publishing, trade secrets and such, and so they had a rule against him publishing his research. He got permission to do it anyways, but he couldn't use his own name. That's why it says student instead of Gossett for the author. You'll see a distribution table in some textbooks that's called student's t-distribution. Well, where does that student come from? It comes from right here. That's the pen name that he had to use. The t-distribution is very similar to the normal distribution. If we go to StatCrunch and we look at the calculators, here under Stat we have calculators, and you'll notice we have these different distribution calculators. And so if our data are in one of those forms, then we can use one of these calculators in order to calculate the probabilities. And so here's normal distribution, and here is the t-distribution. So you can see the t-distribution has a bell shape to it, but it has different peaks. So for example, here we have distribution with what's called 10 df, and it goes from -6 to +6. What if we change that 10 to a 100? Now it's a much more narrow graph. It only goes from -4 to +4. What if we change this to a 2? Now it goes way out past -50 to +50. So how spread out this shape is for this t distribution depends on this value df. And for smaller df values, it's going to be more spread out. And for larger df values, it's going to be more narrow. The t distribution is indexed by 3 different values: the mean and the standard deviation, as are the normal distribution, but we also have a third value, which is the degrees of freedom, or df. The degrees of freedom indicate how peaked the distribution is going to be, or its kurtosis. This top curve is for the normal distribution, and those that follow it are for t distributions with different degrees of freedom. The lowest peaked distribution, the one that is most spread out in the tails, is a t distribution with only 1 degree of freedom. Then the green one, the next one up, is a t distribution with 3 degrees of freedom, and the blue one is with 10 degrees of freedom. So you can see that as the degrees of freedom are increasing, so is the peakedness of our distribution. And it's getting closer and closer to being the same thing as the normal distribution. The degrees of freedom are associated with the sample size. So as the sample size increases, so do the degrees of freedom. That is why we say that for small sample sizes, you should use the t distribution, because here you can see that for smaller sample sizes, it doesn't look like the normal distribution. It's much flatter. But if you have large sample sizes, then they're basically the same thing, so it doesn't matter which one you use, in which case the t distribution still works. Confidence intervals are conducted by taking the sample mean and adding to it t, which is a value from the t distribution, multiplied by s, which is the sample standard deviation, divided by the square root of the sample size. T times s over the square root of n is called the margin of error. And x bar is considered our parameter estimate. So a confidence interval then is created by our parameter estimate plus and minus the margin of error. For a 95% confidence interval, the idea is that you would have a t value from the distribution such that 2.5% is in this tail and 2.5% is in this tail. So we've got 95% in the middle and 5% outside. Let's take a look at how we would do this in StatCrunch. So here we have the customer satisfaction ratings. We have actually 100 customer satisfaction ratings, and we want to calculate a 95% confidence interval. There are 2 ways to do that, and I'll show you what both of them are. You go to Stat and T statistic, and then go to one sample, because you can see here we only have one sample. And then these are the 2 different ways. You can do with data and with summary. If you know what the sample mean is and the sample standard deviation is, you can use the summary. If you don't, then you can use the data. So here we have the data, so let's use the with data. And so you would click on your column that has your data in it, and that's our customer satisfaction ratings column. And then you go to the next, you click on confidence intervals, and then you choose the level of confidence that you want. So if we want a 95% confidence interval, then we have 0.95 as our level here. Then you could click on calculate, and it gives you the results. So here it says the sample mean for this sample of 100 values is actually 23.3. The standard error, if you recall, is the standard deviation divided by the square root of n, is 1.14 or 1.15. The degrees of freedom is 99 because we had 100 individuals, and so 100 minus 1 is 99. The lower limit for the confidence interval is 21.03, and the upper limit is 25.59. So that's how we come up with that confidence interval. That's a 95% confidence interval for our mean. Now, one other thing that you'll notice is under Stat, you have, in addition to T statistics for finding a confidence interval, you also have Z statistics for finding a confidence interval. The steps are nearly identical. You still have the one sample with data or with summary. So why would we choose to use a t-statistic for a confidence interval versus a z-statistic for a confidence interval? The reasoning is in the nature of the problem. If you're dealing with proportions, then you use the z-statistic. If you're dealing with means, then you use the t-statistic. So t for means, z for proportions. And we'll look at proportions a little bit later on in a later chapter. But just recognize that for means, you always want to use the t-distribution, the t-statistic. So for computing confidence intervals, you would use stat and t, one sample, for confidence intervals for means. You'll always use the t-statistic, never the z-statistic. Okay? The reasoning for that is that the t-statistic tends to be more accurate because, as Mr. Gossett found out, with small samples, there needs to be an adjustment. And the t-statistic makes that adjustment. The z-statistic does not. And so in all cases, even if it's a large sample, we tend to always just use the t-statistic for confidence intervals with sample means. So make sure that you always use the t-statistic for sample means and the z-statistic reserved for proportions. Now, I mentioned that you could also find the confidence intervals using summary information. If you go t-statistic, one sample, and then with summary, then essentially it will just ask you for the sample mean, sample standard deviation, and sample size. So if we say our sample size is 100 and our sample mean was 23 and our standard deviation for our sample was like 11, then we can click on confidence interval, 95%, and calculate. And so it will do the same thing. It's just going to use our mean, standard deviation, and sample size instead of the raw data. So if we have the raw data, we use the raw data. If we just have the summary of the mean and standard deviation, then we use that. And so you use whatever you have. And so it still comes up with our confidence interval, 20.82 in this case for the lower limit and 25.18 for the upper limit. So you can find it either of those two ways. So in summary, there are several sampling methods, and typically one method is preferable for a given situation. The distribution of the sample means, or the sampling distribution, provides information regarding the behavior of the sample mean. It gives an indication of what would happen if the sample were collected many times and the sample mean calculated each of those times. The confidence intervals surround the sample mean or sample proportion with the margin of error to indicate an interval that hopefully contains the true parameter. The t-distribution is a correction for smaller sample sizes associated with confidence intervals and hypothesis tests regarding the mean. When working with the mean, we always use the t-distribution in practice regardless of the sample size. We use the z-distribution for proportions. And that is the end of Chapter 9, Sampling and Interval Estimation.